So far, we have learned the conditional expectation function f of x, which is defined as a conditional expectation of y given x. And this conditional expectation will not be the same as y itself, and there will be an error associated between these two, and that error is called the conditional expectation function error. And let us define this error as E, which is defined as the difference between y and m of x. Graphically, again, suppose that you have x as your labor market experience and y as your log wage. Remember, this curve represents the conditional expectation of y given x. Now suppose that this is your data. So this is your data with y and x. Your difference between y and the conditional expectation, so this part, will be your CEF error. And that CEF error will be random because your data y and x are random. It could be this point, or that point. Okay, so we have defined our CEF error as this. By construction, we can easily see that the conditional expectation of E given x is going to be 0. So conditional on any values of x, your E errors on average will be 0. And that property is called the conditional mean restriction. The second property of your conditional expectation function error is that unconditionally as well, the expectation is going to be 0. And this follows directly from the first property and the law of iterated expectations. The law of iterated expectations is saying that expectation of E is given by expectation of conditional expectation of E given x. And from the first property, we know that this part is 0. So in the end, this part as a whole will be 0. The final property of CEF error is that expectation of h of x, any functions of x, times E error is going to be 0. And that again follows from the law of iterated expectation, because that one can be written as this one, and conditional on x, this part is just constant, so it gets out of this expectation, and we have this one in the end. And from the first property again, this part is 0, so in the end the whole part is going to be 0. So what this condition is saying is that the correlation between any functions of x and E error is going to be 0. Because expectation of E is also 0, it means that this multiplication is actually can be interpreted as the correlation. Again, the correlation between any functions of x and your error is going to be 0. Okay, here is another way of stating the same construction. Instead of starting from m of x as a CEF, we can actually just say that y, our data y, is the sum of some function m of x plus e, and this e has this property conditional on x. On average, this e has the 0 mean. And if we write our equations in this way, these two equations imply that m of x is actually the conditional expectation function. Okay, this can be very easily seen because if you take conditional expectation on both sides, then we can very easily see that m of x is conditional expectation function. Okay, so again, we have seen that expectation of E given x equals to 0 is an implication of our conditional expectation function and also the way that our errors are defined. And this condition is called a conditional mean restriction or mean independence. It is saying that E and X are mean independent. There is something that we should be aware of, that is, the mean independence between two random variables are not the same as the full or statistical independence between two random variables. So graphically, let me give you an example. So suppose that you are now plotting X and your y-axis is errors. Okay, so this is CEF error. This is from the same examples as before, and now we are just plotting the error instead of y. And we have seen that on average, conditionally or unconditionally, the error's expectation is 0. And we can easily see that conditional on these values of x, the density of E is concentrated around 0. Okay, so now, although the conditional expectation of E given x is 0, so that E and x are mean independent, by looking at these joint density functions or contours of the joint density, we can easily see that E and x are not independent, because if we conditional on these values of x, then the density of E looks somewhat like this. But now if we conditional on these values of x, then the density of E is different from before. So we can easily see that although E and x are independent, they are not statistically independent. More numerical example showing that mean independence is not the same as full independence is as follows. Suppose that your E is actually the multiplication of x times u, and suppose that x and u are independent. Then in this case, expectation of E given x is given by x times E over u given x. And because we have assumed that x and u are independent, this one is just the expectation of u. And because we have assumed so far that expectation of E is 0, this implies that expectation of u should be 0 unless expectation of x is 0. So this one implies that this part should be 0. In other words, E and x are mean independent. But now, is E and x independent? Are E and x independent? You can see that they are not easily, because E is actually dependent on x. So E, the part that is of part of E is determined by the value of x. So suppose that we compute expected values of E of squared given x, and this one is given by x squared times E of u squared given x. And now again, because x and u are independent, this part is just E over u squared. And E over u squared, assuming that u has a finite variance, is random, this is going to be x squared times some variance of u, and in general this won't be 0, so this one will not be 0. In other words, E squared and x are not mean independent, and they will be in general dependent on x variables. So the variance of E given x is dependent on x, showing that E and X are not statistically independent.